Thank you. I'm going to start and then Dave will take over. So if you have any questions, wait till he's up. Okay. But first, let me ask, how many of you have iPhones? Oh, it's not as many as I thought. Okay.
How many of you have Android phones?
Okay. And how many just have? Who does not have a smartphone?
Mine flips open.
Alright, I thought Sonoma State was in the boonies, but that proves it. I think maybe you don't know what a smartphone is, because I can't imagine that any of you don't have a smartphone. But anyway, so who has an iPod? iPad. Ooh, look at that, yeah.
Any of you who want to work for Apple in the future? Okay.
So anyways, we're going to talk a little bit about 3D graphics, and particularly Apple's iDevices. But this is all about concept. It's not about when you leave here that you'll actually be able to write a program and put it on your iPhone. All right, there's lots of other places that you can get information about that, because 45 minutes is probably not enough time to tell you how to do that. Unless we just showed you an app we wrote, in which case it's relevant. So anyway, so today what we're going to do is talk about iDevices, and not just Apple's iDevices, but any of those smartphones or other smart technology that's coming out. So there'll be other things out there too, like iPads. So all of these things use 3D graphics. And in particular for the mobile phone market, it uses a particular type of 3D graphics. So if you've heard of Opengl, or if you certainly Googled Dave on Google, I guess that's how it would be, right? Then you would have seen the word Opengl several times. But there's another flavor of Opengl called Opengl EX, and that's what we're primarily going to be talking about. It's a subset. It's a smaller implementation meant specifically for that market. Because the devices, like those mobile devices, they don't have as much space as your desktop PC, or even as a laptop nowadays, which would have lots of memory, lots of graphics, physical hardware chips on it, and things like that. So you have to be able to do stuff that will actually fit in that little form factor. And although they're making things smaller and being able to fit more things in that little space, it's still limited compared to the rest of the computing world. And so those are the things that you'll have to take into account if you decide to go write an iPhone app or something like that. So like I said, we don't have time to talk about really how to write the iPhone apps, but just things, the concepts that you would have to think about, and things that you would have to be aware of when you're actually designing your game, or whatever it is that you're going to put on your phone so you can play with your buddies. So there are places to go out there. So if you go out to the iTunes site, there are some classes that you can listen to and hear about how to do this. Or you can certainly go out to the Apple developer website and get information about how to do it, examples and things like that. So there's where you would go for that.
Anybody check those out? Anybody written an iPhone app?
I looked at I think Stanford has a course posted.
They do.
You wouldn't want to bring up some other place's name, but yep, you're right, they do have some. All right, so first we're going to talk about the graphics pipeline and just some of the things that are different for that mobile pipeline. And again, like I said, because it has to be in a smaller implementation, and so they've actually taken out some of the function calls and things that were in the original OpenGL implementation. And we'll talk about the optimizations then again for doing it on this type of platform. So here's the standard graphics pipeline, and basically all rasterized pipelines would look something like this. And we're really being kind of general about it. You don't see a lot of details here, but first of all, almost everything, if you go buy a graphics card for your PC or something, it's going to talk about how many bazillion triangles it can draw per second, right? And the reason for the triangles, simple geometric shape, 3 points in space, and then it fills in the color in between for the pixels, and that's what you get. So if we send it the points, the vertices, and things to draw a triangle, we're going to have to do this geometric transformation and this vertex processing. Now, that's one box, but it does a lot of stuff behind the scenes. And then from that point, it's actually going to go into this other blue box where the rasterization and the pixel coloring is going to go. We're going to talk about those 2 boxes in a little bit more detail, but in the end, you would get something. And in this case, it's the famous teapot. It was the first 3D graphics object that they designed. But you'll see things like the Stanford Bunny or any other object that you want out there, the dinosaur. So basically, the first blue box from that pipeline on the previous page for the vertex processing. Basically, your application is going to call something similar. It doesn't have to be GL draw arrays. There are some other different OpenGL calls that are out there. But basically, what we'll do is it'll send the geometry, those vertices, to the transformation stage. And in this vertex engine, then here, this is where each vertex is going to be figured out where it is in space, because you might rotate space, you might rotate your eye's position, which is going to change where the objects then look, finally when it's in the frame buffer. So there's again some magic here as to when it finally gets into the frame buffer, and then that's what you actually see on the screen. So there's some other processing and stuff that has to happen in between there. And a big difference for the mobile devices of that frame buffer. In a normal PC, that frame buffer would be fairly large, and it would basically map to whatever your monitor size and depth of quality and stuff like that is going to be. But in the mobile world, we're going to see there's some differences here. Okay, where to go? There it is. So it's going to show putting the 3 vertices out in space to draw that triangle, and then basically connect it with the lines. Now, when you draw a triangle or a square or a circle or any of these other types of objects, basically, unless you define other things, they're going to be solid objects. It's going to be a flat, 2-shaded object, but it's going to be solid. So what this means is by determining where these vertex points are in space, then all of these pixels that are inside of here are going to be filled in with whatever color you specify. So again, those are some of the things that you have to specify along with your vertices. So what we have here then is for the rasterizer, this was the second blue box that was in that pipeline. And basically this is going to take, and now that you've given me sort of the space that's actually going to be covered by this object, now I have to figure out which of those pixels do I need to color in. Your choice at this level is fairly simple. I either set the color for that pixel or I don't set the color for that pixel. So there's some interesting things that are actually going to happen here by doing this. So you've got those 3 vertices that you specified, and we can see where these lines are. Like this pixel's totally inside of this, so this will totally be filled in with red or whatever color we chose. But then you have some like this pixel where just a little tiny portion of the line of the triangle goes through there. And so what the system has to decide then is, do I color in that pixel or do I not color in that pixel? So you end up with something, and I like to call it, it's not the official word for it, but I call it stair-stepping. The official word is aliasing. So what you can see over here is that this doesn't really look like a great triangle, right? You have this kind of block, chunky, this is why I call it the stair-stepping thing. So the system had to make a decision, do I fill in this pixel or not? And if that line just sort of grazed it, then it says, well, maybe I'm not going to fill in that color with the pixel. Okay, so if you turn on the anti-aliasing stuff, it'll actually do a better job and make this look more like a triangle. Because what it'll do is it'll take this pixel here, and it won't just make it red. That won't help the situation any. It just pushes out where the stair-stepping goes. But it'll say, well, maybe I'll make it 1/8 red and 7/8 whatever other color of the object is behind it. So it kind of blends the colors of other objects that are near it or the background color. And although it might sound like it doesn't really help, it'll actually help make things look smoother, the lines look straighter. But that's another topic, so I won't go any further into that. So that was just pretty much the standard pipeline, graphics pipeline. And so we have 2 of these flavors. The original graphics pipeline is this fixed function. And we're going to see an example, a little code snippet from a fixed function pipeline program. And then the newer, and I say new, but it's been out for 10 years or so.
Yeah. Sorry, getting old.
Yeah, so the programmable pipeline has been out for quite a while, but I'll still tell you that the majority of applications are, it depends on what space you're in, are written in fixed function. And that's just because there's a lot of applications out there that are still using that functionality and that code base. The real reason for it was absolutely just dead simple for you guys to, as your very first project, write something using that fixed function pipeline. But it didn't give you a lot of control in some cases. And so the programmable pipeline allows you to choose those 2 blue boxes that we just saw a little bit about, and you can write your own algorithm, your own function for that. So you can do crazy things, you can do more detailed things than what the defaults that were already set in the fixed function pipeline. The fixed function means you can't change it. The formula, the algorithm that they chose to do lighting is the way it is. So if you don't like that lighting algorithm, now's your chance to write your own. The problem is you can't just write your own of that one little piece. You usually have to write that whole box of stuff. So you might have to implement some stuff that you really didn't want to implement. go look outside on the web. I'm sure there's lots of examples of stuff. But so those are the two types we have, fixed function and the programmable. Yeah. So we'll see that in some cases, system or devices actually accept both fixed function and programmable. What it means is that you can have an application of either of the two types and it'll run on that platform. What you can't do as an application writer is try to have it do both. It can't do fixed function and programmable in the same program. Okay? So when we get to some other things here, you'll see why they can exist together. Basically anything from OpenGL version 2.0, it says up to 3.0, but the newest one out is 4.0. So, and even the Direct 3D 9 stuff, this is all programmable stuff.
Actually, just to add one little comment, modern versions of graphics APIs, like OpenGL 4.0 and whatever, are entirely programmable, kind of like what you'll see in mobile with OpenGL ES 2.0. There were a couple of versions that were extremely flexible, and so you could do both fixed function and programmable inside of the same thing. And that's OpenGL versions 2.0 to 3.0. At 3.0, and they said, no, you can't use this old trucky stuff. And that's because the 17 people who write graphics drivers got really lazy. So I've been opting.
Don't go to NVIDIA or someplace.
Yes. More up-to-date graphics APIs, like DirectX 11 or OpenGL 4.0, are programmable only. So, for better or for worse, I'm not sure what you guys learned in class, but fixed function is easy, right? You can describe a concept, and there are a lot of function calls that let you see that. The programmable side, you have to learn graphics again, which I have strong opinions about this, but I won't share them while I'm being recorded. So, sorry.
That's okay. Somebody changed the slides and didn't tell me. That's all right. So back to the pipeline. So here what we see then basically for OpenGL ES, the embedded version of OpenGL, and again this is sort of the smaller version of OpenGL that'll fit on the mobile platforms. So the original one was 1.1, which was totally fixed function. That was their first rendition into getting things into the mobile market. And then the newer version is 2.0. So it's on its own update stream, different than the numbering scheme for the regular OpenGL library. And this is the programmable one. So you'll still see devices out there that are using the 1.1 version of OpenGL ES, and then you'll see some of the new devices having the programmable 2.0, but supporting the 1.1. So if there were previous apps that were written, they don't have to rewrite the apps. They have to just write their little translator to, we'll call it a shader to US code. So almost all mobile devices use the OpenGL ES for the embedded version of OpenGL. But like I said, you can't use them both in the same program. They can support both if they set it up that way. So here we go specifically for Apple's devices. And so what you can see is the original iPhone was the fixed function, 1.1. Even the iPhone with the 3G was the 1.1 fixed function. And then when we get to the 3GS, then you see both 1.1 and 2.0. So they implemented the programmable stuff, but again, they had all these apps from the original iPhone that you don't just want to have to rewrite. And so they set it up so that through some internal shaders, little programs, they can actually do that and then run those programs. So again, the newer ones, the iPad, the iPhone 4, they're all using the programmable stuff along with the older stuff. And again, 1.1 only devices. All right, so for the fixed function pipeline, and this is where I said those algorithms, the way it does something, whether it's lighting or whether it's the rasterization or whatever, that's all fixed. You can't change it. The order of things is also fixed. You can't change the order of that pipeline. So, I mean, it only knows how to do a fixed number of things. That sounds like it's really small. It's not. It does know how to do quite a bit of things. But what we'll see is that there's a lot of function calls. And function calls have their own overhead when you're writing apps. So, you know, it was a good thing and it was a bad thing that you had all these function calls that you could specify things, but in the end, sometimes maybe it was too much overhead. The whole idea of the way OpenGL was set up was a state machine. You turn something on and you turn something off. So you can turn on lighting, you can turn off lighting. You can turn on just lots of different things. So we'll take a look at that. So this is a fixed function snippet. It's not a whole program. But what you'll see are all these function calls that are going to specify things. In this particular case, it's an example of lighting. So how to set up the color of those pixels of that triangle. And so you've got all these material properties that are saying for front-facing polygons, these are the colors. And here's my light. And here's what direction it's pointing. I turn on, so I'm setting my state here. I'm turning on a particular light, a particular lamp in a room, and I'm turning on lighting like the circuit breaker in your house. So now I have to do both of those things. And then basically we tell it to draw something. Here's my vertices, I've got 3 of them, and here's my triangle I'm going to draw with all that information. For the programmable pipeline, we're going to see it's a little bit different. Some other terminology that's in here, these things called shaders. This is where you actually get to define the algorithms to do the lighting calculation, or to do any of the things that are in those blue boxes. So these shaders are just little routines that you figure out some kind of formula for, how to actually calculate that. And the thing about this is you need a shader for each of those pipeline stages. So if you wanted to set up both of those blue boxes, you'd have 2 different shaders. You'd have the vertex shader and the fragment shader. You can do one or the other, or you can do both. So here's what that OpenGL ES programmable pipeline would look like. It still looks like the same thing across the top. Right? We send it we are going to draw a triangle, we're going to have 3 vertices, so we're going to give it these transformations for the geometry and the vertex processing. We then go into the rasterization of how it's going to figure out which pixels actually have to be colored in. So that's the same. It's just that now each of these light blue boxes, or royal blue, whatever color you want to call those, you can write your own shader to make your own formula to do this. So you no longer have to follow the formula that the original OpenGL pipeline created. You can do some really fancy calculations, and you can do stuff that has nothing to do with whatever it says. You can write your own stuff. So although we talk about colors and vertices and things, there's a lot of different stuff that you can do in there. So this would be just a snippet of a shader code for the programmable part of the pipeline. So if you just look at this bottom piece, you see it's pretty simple. We got 2 things, right? We're going to set up a color for the vertices, and we're going to set up a formula for how to calculate that. This stuff, yeah, we have to set some values and things like that, some types or whatever, but other than that. So just looking at that little bit of snippet versus the fixed function one, it's a little bit different in the way it has to work. Okay. So that one was much more just like C program, that little shader. Probably looks more familiar than some of those other fixed function words. I was going to say, what page are we on? Oh, yeah. It's yours.
Okay. So, let me just check. How many of you, is everyone taking a graphics class? Or this is just general information? Okay, how many people are taking graphics? I forget how this works. Okay, so you're learning OpenGL? Or you're learning directly?
The API, we're learning more like the actual algorithms.
Oh, excellent. So you're implementing things that could be OpenGL.
Could be anything.
Sure. Could be, yeah. Well, we can find a job for you.
Please.
Right. So have any of you actually programmed with OpenGL? Okay, we're getting there. So we didn't want to fixate on the API, right? A lot of it goes, okay, let me rephrase the question. How many of you have a PC with a graphics card in it? Okay. Any of you that aren't able to actually raise your hand that would have? No, sorry, that's a trick question. Okay, right. In desktop GPUs, particularly the ones that our fine friends at NVIDIA or ATI are pumping out, they're big honking computers onto themselves, right? There's a bus interconnect, but inside of there are thousands of processors. There's obscene amounts of memory, buses that make LA's highways look like they're back roads. Right? There's just tons of computing power inside of there. That's great. By the same token, when you turn it on and start playing, I don't know, Crisis or any of the other kind of modern games, that little disc that goes around in your electrometer starts spinning very rapidly. Now, in the space that I work in, where there are mobile phones, we don't quite have the same luxury. If you wanted to have that kind of computing power, you'd be hauling a cart with a lot of batteries and be able to run your phone for about 2 minutes. Right, so in the space that we work in, we implement the same graphics pipeline, but we've had to make some compromises in order to do it with all the whiny people who go, my phone doesn't last 10 days when I'm not talking on it. Well, it's a small computer now, it's more than just a phone. Except for, I believe the gentleman in the all-right hat is the one with the flip phone. Everything we've talked about so far doesn't apply to your phone, I'm afraid. No, maybe that was a Motorola or something like that? Or Samsung. Samsung. Yeah, previous statement. Okay. So, what is different between a mobile platform and a desktop PC? Well, first, memory is expensive inside of these guys. Right? So this is an iPhone 4 with 32 gigabytes of memory. That's all fine. Well, that's why I have to pay $600 for it. Right? Memory inside of these things is extraordinarily expensive. To get a GPU that has a couple of gigabytes of just frame buffer memory, right, the place where you actually store the image, it would make this several $1,000s and its own small thermonuclear reactor. So we just can't do that. And in particular, Right, as Vicki pointed out, your desktop PC, you've got a chunk of memory that holds the entire image that you work on at one time, right? So you pop a window up on the screen, and there's memory that supports having that all there, and you can draw directly into it. In a mobile space, you can't do that, right? There are two reasons for that. One, memory sucks on your battery. So you have to keep refreshing it, or it kind of forgets what's going on. So we like, in the mobile space, to have small chunks of memory that we can turn off so it can forget whatever goes on with that. The other part about it is a frame buffer is dedicated to a single process, right? So in your graphics and your PC, your frame buffer is dedicated just to doing graphics. Almost all cell phones, for the majority of things, they've got caches, but ignoring that, are what are called unified memory systems. There's a big chunk of memory and everyone pulls bits out of it. So the graphics winds up inside of there and so on and so forth. So we don't actually have this huge chunk of memory dedicated to doing graphics. This is going to cause some ramifications I'll get to in just a minute. The other thing is that also makes the silicon die expensive, right? A square millimeter of, yes, that's right, a square millimeter of silicon in a chip costs a dime. So, you know, most chips are fairly small. When you start getting into the kind of things that, like, well, if you pulled off the heatsink on your NVIDIA while you're wearing your asbestos suit, right? It's a fairly large die. That's part of the reason why the cards cost $200, right? There's a lot of silicon, a lot of technology that goes inside of it. Cell phones, you know, your cell phone you got from a gumball machine? Sorry, I'm not picking on you personally. Right, they're coming in several $100. You don't have a lot of money to invest in those. The most expensive thing in a cell phone now is the screen. Right, the chip inside's a couple of bucks. So they're not going to pay for a whole lot of memory. That does have ramifications in how the graphics operate. We're also very constrained. I used to do things for supercomputers and do also kind of desktop graphics and things like that. I switched to this space because I read a very interesting book. Completely nothing to do with the talk, but I recommend this. There's a book called Innovators Dilemma, which shows why basically companies that do simple, stupid things like I do now always take out big guys. And I was at SGI at the time the guy was writing this book, and NVIDIA and ATI just came in and decimated the company. And he decided to make us the poster child for exactly why this happens. But it's not unique to technology. It happens all over the place. The reason I'm down here is because this is happening again. Cell phones, as you might have noticed, or the guy who has got the iPad, right? Do you use that? Yes, nice to see you again. Do you open that? Well, do you have a laptop too?
No, but I got a desktop. I was thinking about getting a laptop too.
Oh.
But
Does having an iPad actually diminish your requirement or want for a laptop?
yeah, to a fair extent, but it still needs a little improvement, and then it'll totally take out a laptop.
Well, congratulations for being an early adopter. Plus, you're, I presume, a computer science major.
Oh, yeah.
Right? So folks in here who don't think about interfacing with a computer by typing on it with a keyboard and writing programs probably see iPads slightly differently. They think, this is kind of cool. You know, I get to carry this thing around, read the books, surf the web. I sound like a walking advertisement for Apple. I'm not meaning to. It's really a paradigm shift in computing devices. Right? The only reason I have this is because I'm like you and the rest of you, where I still, I delude myself that I still write programs. But theoretically, I am a programmer, and occasionally I hack code. So you do that. You can't do that as easily on these devices. But you know, my mom, she doesn't really want to hack code. Thank God. She doesn't have trouble just like reading email. Before I get too far off track, right? The mobile devices are introducing a lot of things, right? People have high expectations. You'd really be upset if your phone lasted 20 minutes while you're playing a game. So we're certainly constrained on power. We only have a small battery and it has to last a couple of days in case you need to call mom. We're also limited on bandwidth. And this is for two reasons, right? A bus is a collection of wires, right? The bandwidth of a bus is basically counting the number of wires that go there and how fast you can wiggle. We can't wiggle things too fast because that uses a lot of power. And we can't put too many wires down because that takes a lot of space. So we have small buses inside of mobile phones. Consequently, that limits bandwidth. Now, graphics is one of the most bandwidth-intensive things you can imagine doing, right? And when it's implemented kind of the brute force method you find in desktops, right, the amount of bandwidth that's required is incredible. Consequently, when you read the specs for an NVIDIA or ATI card, they'll like, oh yes, we have a 250 gigabyte bus inside of there. Yeah, that's because you're just beating the problem to death with a hammer. It turns out to be extraordinarily effective. I'm not criticizing beating it to death with a hammer. It just turns out that there are requirements, or there are leverages in that space that you can get away with that you can't get away with in the mobile form factor. So, the impact this has on graphics is, because we don't have an entire frame buffer, we can't fire up a GPU and work on all the pixels at once on the screen. Now, you go, well, okay, let's put together what you just said a moment ago, Dave. You said the computer, or the phone, has a unified memory system, so clearly there's got to be a place to put the image. Why can't I have my GPU just talk directly back and forth to that piece of memory? Well, talking back and forth to a piece of memory would be equivalent to using bandwidth, which we've just mentioned, we don't have a whole lot of, and when you use a lot of it, your phone gets hot and the battery runs down. So we've changed using a slightly different algorithm, which is called tiled rendering, and we have what's called a tiled frame buffer. Just out of curious, I know you guys had to go do some research. Did anybody dig up those terms on the web? Okay, no. It's not prolific technology.
Is a tiled frame buffer like what you would use in Mental Ray, where it does like one tile at a time, and then you can break that out between different GPUs?
Yes. Now, correct me if I'm wrong, Mental Ray is a ray tracer.
Yeah.
Okay. So ray tracing is embarrassingly parallel problem, but you'll find that, so everyone know what ray tracing is? No, good, look it up. It's not my talk, man. You know, the other guys come in to do elimination. The ray tracing is an embarrassingly parallel problem, right? What we'll find out in the tiled frame buffer part is we actually take classic graphics and kind of modify it in that direction. So we'll see there's emphasis for being able to do parallelization there. The big desktop GPUs actually aren't very scalable. I mean, they're scalable in processing a whole bunch of pixels simultaneously, but you can't have each pixel processor doing something different. They're getting a little better at that, but it's still not in the nature of the graphics problem. So hang on to that thought, but yes, that's absolutely correct. So what we wind up doing is mobile GPUs, and pretty much, you know, iPhones, Android phones, anything that you walk into a shop nowadays pretty much will have, that's in the US, will have a phone that has a GPU inside it. You go to China, not the same, right? You go to Africa, certainly not the same. Right? But they all have cell phones, and they all love to do this kind of stuff. It's just technology hasn't flown there. Our GPUs inside of cell phones are almost identical to what you have in the desktop. Right? Vicki mentioned Opengl is 2.0. It's a programmable part. Same thing like you can do on your NVIDIA card. Except we just don't work in the entire frame buffer at a time. Now, there are benefits to that. Right? It makes it smaller. You don't use much bandwidth, so you can move your battery. But there will be some detractors, and I'll touch on those in just a minute. The nice thing about it, as I mentioned, embedded GPU has only enough memory for the tile, so that keeps them small and able to do processing, but it does affect how things go. So, you've seen this picture before, right? Animations by PowerPoint. What we've done is we've taken the previous frame buffer we had and broke them up, in this case to 4x4 pixel tiles. What's that?
Never mind.
I'll get back to it.
9 tiles. Never mind how big the tiles are.
I said something, I'm not sure if it was correct or not. Like Vicki said,
It was correct.
that's the benefit of doing it with your spouse, regardless of what you said. You know, you're probably wrong anyways. You take it and break it up into tiles. Each one of these is 4 pixels by 4 pixels. The difference between the previous approach you saw, right? In the previous approach, here, what the vertex shader does, this part of the pipeline is identical. It takes, computes the screen locations where they are, but now it records basically where things are going to lie inside of the tile. So, the animation dropped the dotted lines that were the triangle, but inside of each one of these tiles, where it's going to make me click through them, we record the fact that there's a little triangle in each one of these boxes. Or more specifically, that triangle that we first rasterized intersected these guys. If you remember, there was a triangle that went kind of across this set of pixels. And the way tiled architectures work is they don't rasterize at that point. They basically go, you sent me a triangle, I'm going to see which parts of the screen, which tiles, that triangle intersected, and make a little note. And we do that for every triangle that you submit into the system. Then once you're done doing all that, so your application, at the end of it, you would do what's called swap buffers, or double buffer. That signals to the graphics core, hey, I'm done sending you triangles and squares or any of the geometry that goes along with it. I hope you've done all your vertex shading, you've done all the vertex processing, and binned all this stuff, because now I'd like you to go off and do rasterization. It's at this point then, when each one of these tiles, and this tile is basically the amount of frame buffer space the GPU can work on. You basically read through this list, say, here's the triangle, and basically rasterize that, pretending your window is only these 4x4 pixels. So, in this particular tile here, even though we have information for the entire triangle, it's only going to light up this pixel here. That's the only overlap. Does that make sense? I know the diagram doesn't exactly show it, but there's this intermediate step where we collect all the geometry that you had, figure out where in the screen it's intersecting, and then we do a subsequent step of rasterizing each one of those tiles separately. Now, after binning, right, each tile is rasterized, and only those pixels for that tile are updated. So basically, the GPU will read in all the triangles for that tile, rasterize them, and then write them out to the image in the frame buffer. So your image in the frame buffer is updated one chunk at a time. So you never really get to see the full image until it's completed. Very much like you probably observe with mental ray when it's filling in those things. Once again, if you've never seen a ray tracer in action, it's kind of amusing to watch the pictures go that's good for about 3 beers and 20 minutes. Then I recommend doing something else. So how the tiling process goes, well, it's effectively that. All you have to think about here is there's a kind of collection step. Your application, there's nothing different. It's the same Opengl LES or any other API that you might use for your graphics. You emit all the geometry. It's all collected. And then once all the collection's done, then rasterization goes off to happen in the other part. Now, there are good things and bad things about that. The good things, right? Well, because of doing that, we get to use smaller system memory. We don't need a full-size frame buffer. The disadvantage is, well, we need a little extra memory for all the different tiles that are out in the system memory. So, for example, an iPhone has 32 megabytes of RAM. Right? When you look and it says, oh, it's a 32 gigabyte device, that's actually, as you elegantly put it this morning, the disk drive, even though there's no disk drive inside of it. It's just it's the flash memory that the battery keeps going to retain information for you. But when an application is running, you only have 32 megabytes of memory to play with. And for a tile-based renderer, part of that 32 megabytes is now going to be the frame buffer, the image that's there. If you had a full-blown GPU inside of there, that would be a separate memory space, and it wouldn't be deducted from the whole application token. You have a question?
Oh yeah, are you talking about the iPhone 4? Does that still have 32 megabytes? Or just the iPhone 3G or something?
I think okay, that's a good point, because this moved to iOS 4.0, I'm not sure how big it got for application space.
Because I know, I just have the first Motorola Droid that has 80 megabytes or something.
Okay.
Or at least something like that.
For application space.
Yeah.
Yeah, it might be. I'm a little out of date on how big this actually is for these guys.
Okay.
So, I may stand corrected on the part. Thank you. No worries. Then we go about these things. The long and short of it is, right, we deduct a little bit of space from the application. And in fact, we actually need, familiar with double buffering? You show one image while, okay, yes?
Yeah.
Okay. And for those who aren't in the front row, double buffering is we show you one image while we construct another one. And then when we're finished constructing it, we just kind of flip it around. For page flipping, tons of things. The technology's been around before George has started doing computer science.
1958.
Wait, you were still using crayons, weren't you? Some of the other benefits. As our esteemed colleague there said, hey, some of this can be done in parallel. And this is very true. In fact, one of the benefits of mobile graphics, and why I personally think, and this is on the record by the personal opinion, why mobile graphics will take out people like NVIDIA and ETI is the fact that they're parallel, they're scalable. In fact, they're infinitely scalable. That binning operation I mentioned collects up information about what's required to draw just those pixels. And that unit's self-contained. And so we can basically store that up for every tile on the screen. And if we put enough graphics processors inside of there, we can churn through tiles in a very parallel manner. Desktop GPUs can't do that, right? So you can stick another GPU card inside of your box, but it really doesn't apply much into the scalability part, right? So if you've got NVIDIA's SLI technology, basically they do this old TV trick of interleaving scan lines, but both GPUs are doing effectively all the same work. You can only do that so much, right? You can kind of scale through, but you're doing kind of pixel level. If we have 1,000 tiles on the screen, and the GPUs are small enough, we can put 1,000 GPUs in there and crank through. That's all great. So there's a lot of stuff. But one of the bad things about it is there's additional latency. What are you
Just
doing?
keep going.
Okay, I'm going. There's additional latency added in. Do you guys know what the term latency means? Yes? No? Okay. Well, if you don't, I brought a slide along just to help everyone get on the same page. Right? Latency is the delay between when you generate a frame and it pops up on the screen. So I'll wager a guess here. Somebody in this room has probably played video games.
No.
Okay.
No way. What?
And I feel safe in the Tenderloin. Right. If you can tell a good game versus a bad game by how responsive it is. If you see an image, right, so let's say you're doing the very first-person shooter thing, right? You line up with some guy and you pull the trigger, and oddly enough, he doesn't die, right? Or he doesn't take damage. Or maybe he gets hit with a marshmallow. We make this family-friendly. Long and short of it is, right, I've looked at an image of the screen, I've made a decision and asked the system to do something, right? Take and shoot this guy with a marshmallow. And oddly enough, it determines that I didn't hit it. And you go like, well, why is this? Clearly it was on there. because the image you're presented with and the data that the application are doing are slightly out of sync. And this is this concept of latency. Now, it turns out that this is actually a very large problem. The human visual system runs at 50 hertz. So the magic number you have to hit is 50. Oddly enough, most monitors nowadays, they don't have 50 as one of the cycle times, like you get 72. There's the refresh rate of your LCD, but the long and short of it is, as long as it's above 50, you as a human are fooled into thinking that this sequence of discrete images looks like continuous streaming, right? Oddly enough, movies run at 24 frames a second, but they still trick you into thinking that's fluid motion as well. Now, latency would be, I'm looking at one image, but the application is some point farther in the future, and how this affects things. Immediate mode renderers, like your desktop, are actually pretty good about handling latency. There isn't a whole lot that goes along there. In fact, it looks a bit like this. In desktop, we work on a particular frame. So we're going to render frame n. The application samples time, updates all the state variables. So this person's run, he's fired marshmallows, and renders the entire scene, and then does the buffer swap. So it's at this point you actually get to view the image. And then we start working on the next scene. So what you're looking at while we're rendering this frame is only one frame apart. Does that make sense? Right? I draw this picture, and at this point, this picture is exposed to you, and I start working on the next frame. So my input is fairly close. If we're doing this at a good frame rate, which is usually 60 hertz for games, right, that's 16 milliseconds. Humans really aren't that fast. Of course, any of you want to take me in my 350Z, we'll see how reaction time actually goes. But right, that's pretty quick. And it turns out that that's fine for the human system. It's fast enough to convince you that everything is continuous. If it goes... If it goes longer than that, bad things happen. And it turns out that actually just the jitteriness of the screen can make you physically ill. The US Navy and other people I've worked with have discovered this because if latency is bad enough, it'll actually cause you to pull chunks inside of a simulator, which is unpleasant, but it's odd that just stimulating your visual system can cause a physical response of that nature. Right? The same thing in games. Tile renders, now, why is this important? A lot of apps on side of cell phones generally aren't interactive until Apple came out, and other people, now Android certainly, where gaming is really becoming a prominent application space for it. And people want to take their Xbox 360 games and other things like that, take and have those available inside of your device. Well, that's great, but Xbox 360, Sony PlayStation, the Wii kind of, but not really, they're goofy. They've got a different model for doing things. It's a different conversation. Right, they're doing the high or the low latency situation where they only have one frame of latency. For ours, we have to, application runs and we get the swap, and it's only at that point that we can start working on rasterizing the frame. Now, the one part this diagram doesn't show very well is the fact that it's only at this point do you actually get to begin to see the image, right? Rasterization is where we generate it. So there's kind of another swap. This is a software thing. There's a hardware display piece that actually should go here that says, here's where you get to see the image. Now, what's the problem with that? Well, here you're looking at frame n. Well, if we go, there's frame, we're binning frame n+1, the application is updating. By the time you actually get to see it, you're 2 frames behind. If you're running at 60 hertz, that's a 30th of a second. That actually is noticeable to humans. And so you do run into problems more inside of the space of people having difficulty keeping up with the game, faking missed shots. How's it manifest this out? If you look at a lot of first-person shooter games on devices, the enemies don't run around that much. Keep that in mind. Okay, I need to zip this up real quick here, but basically, what's the problem with latency? You're not seeing the image the application's processing. And this causes delays. You're going to have a bad user experience. People will be disappointed with how it all fits together. So, how do you do that? 2 things. First, there's this myth in computer graphics that there's something called constant frame rate. There is absolutely nothing like that. Right? It takes as long to draw a frame as much stuff as you want to stick in. So if you draw 1 triangle, it'll go very fast. If you draw 10 million, it'll probably take a bit longer. The problem is, if you make assumptions that, I set my monitor to 60 hertz, I'm going to get a frame every 60 hertz out of it, that's not going to work. So you need to keep close track of time. You also have to track velocities and things like that very well. Like you say, a little physics never hurt anybody. When you're doing gameplay, and I assume that any game anyone wants to write is going to be first-person shooter. Anyone who's going to write a Sudoku puzzle, see me outside, we'll have a little chat. Right? First-person shooting, right where it's at. No. You need to track the physics. The gameplay on mobile devices needs to be tweaked a little bit better because of this latency problem. And, you just want to keep this in mind. For my ray tracing friend, you'd be living in a world of hurt if you tried to do ray tracing and the latency there. It's getting better, by the way. The other part, render as efficiently as possible. And I'll give you just a couple of quick things on that part. Specific to the iPhone platform, iPhone uses this technology from a company called Imagination Technologies. Effectively, most machines, so you'll certainly talk about in the graphics class a technique called depth buffering, if you haven't already. And it's a way to basically figure out what's in front of something else. Every triangle you send has a distance from the eyeball. We just correlate those and figure out which one's closest, and that's the one you see. These guys, well, that particular technique is something called shading before visibility. We figure out a pixel's color, and in that process figure out how far from the eyeball it is. And then after we do all that work to figure out the color, we determine if you can see it or not. It's not the most efficient way, but once again, it's nice and brute force. It turns out, however, iPhone's done a little differently. These guys don't use the depth buffer. They actually figure out, you give them a collection of triangles. They do a bunch of algebra. They get little guys in there with pencils and erasers, figuring out how all the triangles intersect. And for every pixel, they determine which triangle you see first. Then they go off and do the shading. So that's actually quite an efficient way of doing things. It allows you to, you don't have depth buffering, which can have problems. It allows visibility before shading, so it makes it more efficient. You only compute the color once. One caveat is there's this technique called alpha blending for doing translucent objects. If you haven't got there in graphics, I'm sure you'll discuss it. Alpha is the important fourth color after red, green, and blue, right? And because if everything's opaque, you only have to figure out one solution. But if you rely on multiple pieces of geometry to figure out the final color of a pixel, this guy runs into some problems with getting that. So you go, hey, I'm going to make all my characters have these really cool electric suits that are somewhat transparent and have 100 of them running around the screen. Yeah, your game's going to go really slow on the platform. The last thing, last slide, and the best part is, you can help your applications run very efficiently on these kind of platforms by drawing your geometry from the piece closest to the eyeball to the piece farthest away. And this just helps optimize the system to keep track a little bit, going, hey, I know this guy's pretty close to the eye. I get to do a real quick check to go, is this farther from the eye for every pixel? And if it is, I don't have to do any more work and throw it away. That makes things work really good. In fact, this is a nice algorithm to work on any kind of PC, any graphics application in the modern world. There's something called early Z code. Early Z code that helps get rid of this. The downside to this, sorting geometry is a pain in the rear. Because you have to sort, basically you need to know where this guy is and doing that, but there's a lot of different technologies and algorithms to help you out. Good stuff to go out and research. So having said that, we have a minute and 35 seconds for questions. But I'd like to say thank you. Sir, please.
So do cell phones have the same frame rate as desktop monitors?
Generally speaking, no. They're usually run about 30 hertz if they're run that fast. They don't need such a fast refresh cycle, and cranking the LCD at that rate does cause problems. Now, having said that, netbooks and other things are heading in that direction, but currently mobile devices that are battery powered don't run quite that fast. Sir?
Are there any mobile devices that have multiple cores?
Yes. What?
Are there many that are
The stream is coming out. I mean, I don't know exact things. Okay, the answer to that categorically is yes. And the more devices are coming out, that you're seeing a lot more of this. So there's a new chip that just came out that has I think 2 or 4 CPUs inside of it and a whole bunch of graphics cores as well. I mean, it's a really powerful machine for doing that kind of stuff. So you'll see these guys getting better and better fill performance. So you'll be able to fill lots and lots more pixels. So the iPod's a good example, right? It has a really high resolution screen. I'm willing to bet, I don't know for sure, don't record me saying I'm speculating on Apple technology because I don't know. But my guess is they probably do something like that. So, gentleman in the back?
Have you developed any apps in the App Store thus far?
I haven't done anything public.
Okay.
I have written some Opengl ES application for the phone, but I don't have the time or the frijoles to actually go out in public on that part. So, sorry, not being a charlatan, but no.
So if you use single buffering with the tile render, can you see all the tiles be drawn on the screen, or do they use double buffering so you don't see that?
So, excellent question. The answer to that is Opengl ES only does double buffering. There's nothing that limits the hardware from doing that. Basically, there's a device controller that scans out the frame buffer. And so you could watch these things being populated on the screen. Generally, systems aren't architected to do that. But, yeah, Opengl ES doesn't do single buffering. Anything else? Cool. Well, thank you all very, very much.